Thank you very much for the introduction. Right, as Shaya just said, my name is Sebastian. I'm doing my PhD in a group of Professor Madsen at the TU of Vienna. And I'm funded through Infineon Technology and then AI for DI Europe grant. Okay, so what's predictive computational material science about? I guess everybody in here who does material science will agree that we're looking to get predictive answers to real-life questions, such as what material has what property, how and can we even synthesize it, and how do materials behave under different conditions, for example, during processing. Recently, there have been several enablers that have pushed forward this field. Not only the constant computational, increase in computational power, but of course, we're getting really good with technology design and development, and we're reaching a level where the current simulation methods don't provide the required detail of understanding to really push forward there, which leads to a bunch of industry involvement, which is also why I'm here. And of course, the rapid development of machine learning methods has given the whole field a push, not only because it makes the prediction problems, so going from material to property easier, but also because I think for the first time it's making the design problems, so going from a property in a systematic way to a material, also possible slowly. So how does this usually work? Thanks, Kimin, for the introduction to DFT codes and DFT. So usually you start with doing some ab initio calculations, right? For example, using PySCF. You use them to do some sort of statistical mechanics, and then you arrive at a property. However, for many, many situations, doing this directly with ab initio codes, this is still far too costly. So for example, if you want to explore a potential energy surface of a low symmetry structure, or if you need really, really long trajectories because your properties are hard to convert, then you need lots and lots and lots of calculations, which makes it unfeasible at some point. Now we've come up, so the community has come up with several ways of going beyond that, from very, very simple parametrizations such as a Lennard-Jones model or a Morse model, to harmonic approximation to the potential energy surface, introducing even higher order corrections, and then even up to very delicate and high performance force fields like ReaxFF, which perform remarkably well in the use case they're designed for. But they transfer really poorly, and you cannot really systematically improve upon them. So in 2007, Bela and Parinello have published this paper, which I think was one of the first, if not the first, application of machine-learned force fields in material science. The idea here is essentially very simple. So you take your Cartesian coordinates of your atoms, so x, y, z for every atom in your cell. You generate a descriptor for every atom. So essentially you study the local neighborhood. And then you throw that into some kind of machine learning algorithm, such as a multi-layer perceptron or a Gaussian process regression model or whatever. And then you arrive at some atomic energies. You add them up. And this is the unphysical part. I was talking to some of you and told you we're doing one thing that's a bit unphysical. This splitting into single atomic energies, that's a bit unphysical, but it works and has been proven time and again that it does. And then you add them up and you arrive at the total potential energy. And the cool thing is, if you build your descriptors properly, you can encode translational and rotational symmetry in there, which is required because, well, nature is translationally and rotationally symmetric in most cases. And also through the splitting of the energy in atomic energies, you get permutation symmetry. Now, since then, a lot has happened. And nowadays, there's a lot of choices that you need to make when you derive a machine learned force field. What descriptors do you want to use? You want to use local descriptors, global ones? Do you want to use TensorFlow, PyTorch? Do you want to write your neural network framework in Fortran? Everything is possible, and many, many more questions. And today I want to talk a little bit about what our choices were, why we think they're good, and what we're doing with it. So first of all, we're not really using a machine learning framework. We're using Google JAX. And that's kind of an autograd framework. So it breaks down your code into very simple instructions with Jacobian vector product rules. And through application of the chain rule, you can then take the derivative of arbitrary functions as long as they're written consistently with the style of requirements of JAX. There's some added advantages, such as just-in-time compilation. It basically trivially runs over GPUs and TPUs and parallelizes very smoothly. And if you're interested, there was a great talk by Jake Vanderplas, one of the guys responsible for JAX at SciPy 2 years ago, which I can highly recommend. I have some examples of what autograd or automatically differentiable means here. A very simple first example is like you have a linear function which has some slope, and we also have a simple trigonometric function, a sine, and then we can just go ahead and calculate, does my laser pointer work? And calculate the gradient of the function, and we can plot the function and its derivative, and indeed, we see the slope, the orange curve, or the orange plot is the derivative. Yay, it's 5, that's great. And the derivative of our sine is a cosine, which is also great. But we can also do it for more complex functions, such as a Lennard-Jones potential in this case, where you essentially write down the expression for the potential energy surface, or the potential energy, and then you can just take the gradient, put the minus sign in front, and you have the forces. And so if, for example, we look at the energy and the forces of this cluster that you see here in the top right of the plot on the right-hand side, and we move this one atom up and down a little bit, then we can immediately obtain the potential energy in blue and the forces in orange, and indeed it's consistent with what you would expect. There's a minimum at no displacement, and the forces pull you back into equilibrium. But enough of this little sideline. I was talking about our choices. We're using a flavor of spherical Bessel descriptors, where you essentially use a weighted density around each atom. You project that onto an orthonormal basis set, and then you build the power spectrum of that. So you take care of all the symmetries. And essentially, you can see here on the right, if you ever wondered what your computer sees when you do those things. So these are some of the descriptors. Right. Next up, there's there's some architectural choices, and here we're kind of classic. Like, we took this pyramidal, fully connected approach, where we have added in some unique features. So first of all, it's end-to-end automatically differentiable due to JAX, which is great because it means we can train not only on the energies, of which you get 1 per DFT run, but also on the forces, of which you get 3 times the number of atoms per DFT run. We've introduced a learning rate scheduler. We're using the swish activation function, which is actually necessary because if you train on the forces, you need the derivative of the loss function. So you need additional requirements with regards to smoothness of your activation functions. We also have some normalization layers in there. And in the end, you arrive, as Bela has already shown in 2007, from some Cartesian coordinates, you arrive at some potential energy in the end. And so the question is, does it work? Well, yes, it does. Our first pilot system were Ionic Liquids. We've seen a few key outcomes here. First of all, training on forces is absolutely necessary. If you do that, then you can achieve almost ab initio-like precision. So the statistics are really good that we get here. And what was really surprising in this work, because it was Ionic Liquids, is that you don't really need to take into account long-range interactions. I'm not saying this is a general truth, but in this case, they just didn't matter that much. Right, but now let's get to some actual use cases. So I talked a little bit about higher order corrections and higher order expansions. And so since everything is differentiable, you can trivially obtain Taylor series expansions through essentially nesting Jacobian vector products, as I've written in the top box here. As we're doing Jacobian vector products and not calculating the whole matrices and higher order objects, there's no exponential scaling. So it does slow down a bit as you increase the order, but it's totally manageable. And the cool thing is it's accurate to within machine precision essentially. So this is not some approximation. It's literally the Taylor series up to order 4, which is pretty cool. And so we wanted to see, are they any good? Because people have been using them as surrogate potentials for quite some time. And we trained a neural network force field for a silver cluster, which you can see here in the middle plot on the bottom right side. We trained on 2,000 structures for 1,000 epochs. We got really good statistics here as well. So a force MAE of 8.7 milli electron volts per angstrom, as compared to a standard deviation in a training set of like almost 1 electron volt per angstrom. And so the neural network force field is a really good representation of the DFT backend that we're trained on here. And so we can assume that it's the ground truth, so to say, and build a Taylor approximation using this, because taking Taylor approximations of DFT code is not yet possible, I think. And now the graph here on the right-hand side, it might need a little bit of explanation. So that's the error in the force as compared to the ground truth of your fourth order approximation as a function of the displacement. And now why is that important? So Taylor expansions are polynomial expansions. And polynomial expansions are local by nature. And especially if you're sampling in a very, very high dimensional space, such as, well, here, kind of here too, yes, then you will always have some elements of the sample that you've drawn that are way out. That's just a matter of fact. And polynomials are notoriously bad if you move further away from where they were set up, so from equilibrium essentially in this case. And so what we can see here is indeed, as we move to the right here on the x-axis, which means larger displacements. There's my laser pointer, great. Which means larger displacement, the error actually increases over exponentially almost. So this is a double log scale, and it turns horrible pretty quickly, and the explanation is pretty clear. So I have a very simple picture here. If that's your potential energy surface, and you put like a parabola in here, and you move to, you move outside of, yeah, then you're done for essentially. And so what's the takeaway here? Are they necessarily bad? No, they're not necessarily bad, but you need to be aware of the limitations. So if you see somebody doing a harmonic approximation at 2000 Kelvin, just, take into consideration whether that's like a good thing to do, or maybe it's not, So now moving on to what's actually the topic of my PhD. So hafnia, it's gone again, okay. It's a well-known high K dielectric in industry, and there's a ferroelectric phase, and there's a bunch of other phases, and the phase structure is really complex. And the stable phase is essentially determined by an interplay of numerous factors, and we're most interested right now in temperature. And to treat temperature-dependent effects, you need some sort of framework. And since, unfortunately, the cubic phase here is mechanically unstable, we need something fancier to do that. And so we went with effective harmonic potentials, where the goal is essentially to find a sort of quadratic potential which describes the relationship between the displacement, so how far am I from the equilibrium, and the force at a predefined temperature. Now there's the finite displacement approach, where you use a very small displacement around the origin, and then you derive your force constants. And if your potential energy surface looks like the dashed black line here, then your finite displacement second order potential will be a downward sloped potential, which indicates mechanical instability. However, if at the temperature that you're interested in, your displacements aren't super tiny, but instead follow a distribution, let's say the one in gray in the back end here, then the orange curve would be a much better approximation of the potential energy surface at this temperature. And so that means that you have a temperature stabilization effect here, because the orange curve, as you can see, is not downward sloped anymore. And as you might have maybe already guessed, this is kind of a self-consistency cycle. And And we've introduced the neural network potential into this self-consistency cycle. So we start out with some kind of initial density, sample our displacements from there, use DFT to obtain the forces and the energies. Then we get a new effective harmonic potential, from which we can get a new density, and so on and so forth. And you could close the loop here, you know. You could close the loop here and be done. But the problem is, if you move to lower symmetry structures, if you move to something like a monoclinic phase, that's just not feasible anymore, because there's so many different permutations you have to consider that are hard to converge as well, that it just doesn't work. And that's why we use this neural network potential here as a surrogate. So we continuously, like after each iteration, we train our potential, we see if it's converged, and if it's converged, we just cut out the DFT backend and use the neural network force field instead, which is a lot cheaper. So how much of DFT data do we actually need? We tested this using cubic hafnia, and we see that after about 200 runs, there's no further improvement by adding more data. So we decided to go with about 200 DFT runs. But we also saw another thing here, and that's really interesting. So if you have two atoms that are very close together, there's many right answers of what the force on those atoms should be, but 0 is definitely not one of them. And we actually saw that if we remove all of those situations from the training data, the neural network just predicts 0. And since we cannot get all of the situations where those atoms are close together in the training data, and it would also be quite meaningless to do so and a waste of resources, we went with a much easier solution. So we included the repulsive part of a Morse potential, which in the same case, so the plot here shows, this is like truth versus prediction, shows of a model trained without any high forces, evaluated on the structures with those high forces. And just by adding this simple term, the quality has improved drastically. And now, of course, in the production quality run, we include all the data that we want. Okay, but now let's see what we're actually using it for. So as I said, we're kind of interested in the phase transitions, so we need to be able to describe multiple phases. And so we've then did essentially the same thing. So this cascading technique, let's say, we did here. We also did for tetragonal, and it turns out you only need 75 tetragonal data points to get like a very good representation of both your phases. And we also get very good statistics here with force MAEs below 100 MeV and energy NeVs, energy errors on the order of 3 MeV per atom, which is which is really good and comparable to what you get if you just change your exchange and correlation functional. And that at a cost several orders of magnitude below DFT. And now let's look at some of the validation, or because we're interested in phonons or in temperature-dependent effects. So just the statistics are maybe not the right thing to look at. So these are the finite displacement phonons of your cubic hafnia. And we can also do finite displacements with the neural network as a backend. We have an interface to ASE, which is very useful, I think, for these kinds of things. And it turns out, yes, we have a pretty decent agreement here. But since we're fully automatically differentiable, we can do something much, much cooler than that. We can directly evaluate the dynamical matrix at a given Q point through vector Hessian vector products, which in essence is just a smart concatenation of Jacobian vector products. And this also works remarkably well, and I think is a pretty cool result. So I love this picture a lot. Right, so we've confirmed that it works for the forces, for the energies, and we get nice phonons, which we kind of already guessed, but it's cool to look at. Now, what do we see if we apply it to the phase with temperature now? We see a continuous hardening of this soft mode, which indicates that your material is becoming more stable. And at around 1500 Kelvin, we have no more imaginary frequencies, so the material becomes stable. And this is also a really cool plot because you can make this with the neural network potential in like 2 hours or so. And with DFT, it would take days. Right, and so of course this is also something that's cool to look at, but it doesn't really tell you much. And so I thought I'd bring along something that you also know from like real life, thermal expansion. So first of all, we validated again the neural network against the DFT results for the cubic case, and we see here. So in the dashed line, you see the DFT result, and in the solid line, you see the neural network result, and we see a pretty nice agreement, let's say. Then we used it to treat the tetragonal phase, and we also found some experimental data which to compare it to, and it compares really favorable to experiment. The only thing that's a bit concerning here is that we're underestimating the volume, but we're using PBE functional, so this is only for the for the DFT guys here. So that was a bit weird. So we decided, okay, we have this methodology to really quickly build like neural network potentials and apply them. So we also did it for PB Sol. And there we see we underestimate both, but we still massively overestimate this volume quenching when going from tetragonal to cubic. There might be, we're currently investigating this. We think, or we're quite certain that we haven't messed anything up. And one of the possible reasons is that the experimental phases of cubic hafnia might be oxygen deficient, because at 3000 Kelvin, it's really, really difficult to keep a track of your oxygens. And yeah, that's what we're currently looking at, and I think it's super exciting. Right. What we're going to do afterwards, well, we can do other phases. We can do new materials, interfaces. There's some people in my group who are already doing surfaces. Or we can go, deeper. We can go more into detail with this idea of direct evaluation of the dynamical matrix. One of my colleagues is working on deep ensembles for predicting uncertainties and then kind of turning this into an active learning scheme. But it's not yet published, or it's in its early shoes. And of course, which really lends itself to it is molecular dynamics. We're also looking into that a lot. The code is freely available here, fully open source, with a bunch of examples. I'm happy to provide any, demos of the things that I showed you here. If you contact me through email or LinkedIn or whatever. And we're really happy for any discussions and for new ideas of how to use automatic differentiability in our research. And I think now it's a bit time for questions, right?
Thank you, very nice talk. What I would be interested in is, how does it compare to linear models like the atomic cluster expansion, which is very popular in the field of material science at the moment?
So could you give me the general?
So the idea there is basically that we just have more advanced descriptors, and then it's sufficient to use a linear model to fit the interaction, which usually has a huge performance benefit compared to the neural network. So I would be interested to understand what's your motivation to use the neural network.
That is a very good question. Unfortunately, I can't answer it right now because I've not used cluster expansion models. I guess it depends a lot on the material you're studying and on how the potential energy surface looks like. Similar as Taylor expansions, where it works for some cases, but for some it doesn't. And maybe the neural network potentials are a tad slower, but you don't have to be so careful with where you apply them, I think. But we can talk afterwards if you're.
Thank you.
Yeah.
Any other questions? I had a question. Initially, you mentioned something about ionic liquids, where this is used, or you used it. What were you bringing it? Was it something that you used with ionic liquids?
So I was kind of tangentially involved in that. Okay. I did the long-range interaction stuff on it.
So I know, I'm not that familiar with ionic liquids, but I've seen people use like classical mechanics systems models for it, like classical force fields. How does it compare?
You can't. I mean, if you have even among the very specialized force fields, classical force fields, you get really, really large deviations to your DFT results. There's actually a case study on that precisely in the publication, which I can send you if you're interested, where we kind of show that you either need to use DFT or you need to use something that captures DFT level effects to correctly predict how your ionic liquid behaves.
Right. And I'm also curious, how many data points do you need when you train this model, and what kinds, like, are you looking at like different configurations, different?
For the ionic liquid,
Or generally,
yeah.
For
So
Ionic and the other systems you were
it
studying.
depends a lot, right? So since we're training on energies and forces, it depends a lot on the cell of your on the size of your supercell, right? Because you get more forces, you get more information. But I've trained the neural network potential that I've used for this in total then on around 300 structures containing 200 times containing 192 atoms and 75 times containing 216 atoms, if I'm not mistaken.
And how well does it generalize outside of those configurations that you train on?
Well, so since this is a kind of a stochastic approach, right? And we get results that are in great agreement with DFT, even though we use different configurations, of course, right? We can kind of infer that it might work very well. But of course, so I'm not a cheater. The graphs you see here, they're all on validation and test data. So this is not training data.
Okay.
Yeah.
Right. Any other questions?
Hey, thanks. That was very nice. But so my question is, when you say you're training on energies and forces, is the output also energies and forces together, or is it just energy and then you differentiate it with jacks?
So that's a good question, also kind of philosophical, which we had in a group meeting recently. So we have one model that outputs energy, and we can take the gradient of that model and it outputs forces. And during training, we do the exact same thing. So you can get both things out of the same model. So it's consistent with each other, and it's kind of the same model because you don't really lose much except for the offset, if you like the origin of the energy, if you take the derivative of it. And so I think it's like the same model which gives you both. I think that would be my final answer.
So then the interpretation is that the input is 1 energy and then 3 force values?
So yeah, the input is positions type cells, and the thing that we optimize against is energy and 3 times the number of atom forces. Yes.
Okay.
I mean, you can of course vary this. You can leave out the energy, you can leave out the forces, you can add in the stress, you can, yeah.
Just very short question. Have you left out the energies once and seen?
Yes, yeah. So if you leave out the energies, the only thing you have to do is you have to fix the offset. And if you treat systems that are unique in this origin, so if you treat one volume, for example, then it works almost as good as if you add in the energies. This becomes a little different if you have a system like I do, where you have different volumes, because those, of course, all have 0 forces at like their respective equilibrium position, and so you need to add in a little bit of the energy to the loss function there to ensure that you capture this effect.
Yeah, wonderful. Thank you.
Any other?
Hi, thank you for the nice talk. So you mentioned your software is rendered as a open source software.
Yeah.
Can you provide the name or reference, or should we contact you if we want to use that?
Sorry?
Do you have the name or reference for your?
Oh, sure. So So hold on. So it's available here at this GitHub. It's called Neural IL because we started with Ionic Liquids, and it's a neural network. We might need to change the name soon because we're using it for a bunch of things.
Okay, thank you.
Sure, you're welcome.
I didn't expect it to be that loud. So you said you did the long-range interaction work.
I'm also going to give the same disclaimer in that I don't know a lot about liquid ions or like the size of these systems. But how did you take those into account with a Baylor and Parnello inspired architecture?
Yeah.
Because it seems
No,
that's a difficult problem.
No, we actually you can add as many terms as you like to your energy expression in the way that we've devised neural, and we've just went ahead and added in a charge equilibration scheme called SEND, where we we used some neural networks to predict the electronegativities, and from those we obtained charges, and then we equilibrated them. I should have probably put the QR code for the paper up as well. The details are in there. I don't recall them by heart, but yeah, it's not Bichelmaier for charges. It's Bichelmaier for electronegativities.
Okay, that's that paper that came out in like 2020 or something like that.
Yeah, so there's one by Baylor as well with his I think it's called the 4G HDNNP or something. Yeah, exactly.
Okay.
Yeah, exactly. Yeah.
Okay. Thank you.
Any other questions?
Hi. Sorry about that. I thought it was interesting that you tried to incorporate like some physical intuition to bias against the non-physical circumstance of overlapping atoms, or that you couldn't train on once you saw that was a weakness of the trained network. But can you talk a little bit more about where that comes into play? Was that like a something that you incorporated into the training, or something that you applied to the resulting force field? And given that, are there other heuristics or physical intuition that you might be able to apply, or would it be like, can you comment on what would be safe or unsafe to incorporate, and how?
So first part of the question, the Morse potential, I think it has like 3 parameters, if I'm not mistaken, and we also have like a cutoff radius, right? Because you need to smoothly go to 0, and those parameters are all part of the training. So as I said, with the SEND model, you can just add any energy expression that you want to the model, as long as it's differentiable, and then you can build your own stuff, whatever you like, or whatever you think is good for your problem.
The final force field is like the superposition of the neural force, or the neural network force, or potential field, and then you add to that.
Exactly. Yeah. Well, it's trained like together. So what we don't do is we don't subtract like some components, which was very much done in the past. We don't subtract like the Morse potential forces from our training data and then train on that. No, we train like to get both things together. It's one model that's being trained then. Yeah.
Is that unusual? That sounds interesting and unusual.
I don't think it should be unusual. I don't know how it's done in detail in other codes. I'm sorry. With regards to what's safe and what's not safe, I mean, you should take care that it's smooth, sufficiently smooth, because you don't want any kinks in your forces, or like discontinuities in your forces, right? And it should make at least halfway sense that you could get it out of a local kind of view on things if you're basing it on the descriptors. But aside from that, go wild. Like we're super happy for any new ideas on how to incorporate different effects if they're necessary to be incorporated. Yeah.
Did you find that the neural network trained substantially differently when you included that repulsion, or did it arrive at a similar answer, but with a resulting force field that was just better?
That's a difficult question to answer. Okay. So the statistics are significantly worse, especially the RMSE, because that's more heavily based on outliers. If you don't include the Morse model, but I haven't compared it like bit by bit. Also, I don't think I don't, with it all depends a lot. The precise predictions depend a lot on your weights and your random seed and everything. So I'm not super sure about that. Sorry.
All right, let's thank Sebastian again for the great talk.